Hi, everyone. Thanks for the introduction and thanks for the invitation to give this presentation in this nice seminar. My name is Schäfer and I'm a postdoc in the Julia Lab at MIT, advised by Alan Edelman and Chris Rokarkos. And I will talk to you today about how we can integrate machine learning models into differential equations for automatic discovery of missing physics, very similar to what Vinicius just told you, and also for optimal control. And first and foremost, I want to acknowledge also all collaborators that contributed to the things that I will present to you today. There's, of course, the whole SciML team, which is in the meantime a lot of people, which is led by Chris Rokarkos. Then we have Yingbo, who contributed a lot to all sensitivity methods that are used to compute gradients of for the optimization routines. And Julius, in particular, developed data-driven DiffyQ, which is one of the packages that we will see later in more details. And besides the SciML team, there are also people in the Julia Lab that highly contributed to this work. Some of them are also in the SciML team, and also other collaborators that contributed to the modeling aspects. I want to give you a quick overview of what to expect in this presentation. So I will show you some of the techniques basically that we use in scientific machine learning, including universal differential equations. We will discuss a little bit some details for automatic differentiation in these scenarios. And we will see these sparse system identification techniques such as SINDI. And I think in general, there are typically two ways how you can do such a presentation, or maybe even more. But one way would be, you can write everything from scratch. Obviously, that's will have a limited scope and might be easier to parse, but also it leads to less performant code, and you can't do nice examples, I guess. And in this presentation, I will base it highly on existing packages, in particular tools for solving differential equations like ordinary DiffyQ. We will use machine learning tools like LUX and Flux. We will see some of the differentiation tools, which are very important for all this work. And then also some optimization tools Optim.jl. To give you just a feeling of how many packages we're going to use. So these are all packages used in the following parts. And you see, right, this involves differential equation solvers, some optimization tools, and a lot of tools for computing derivatives. And there are a lot of nice existing resources out there. Large parts of this talk will be based on the automated discovery of missing physics tutorial. Also, the SciML sensitivity documentation has a lot more details that I can cover in the following. So it's a nice resource to look up more details later on. And also Chris gave actually a very nice workshop, 3-hour workshop at JuliaCon 2020 that has also, many more details and is still very timely, I would say. For the rest of this talk, I decided to focus on one basically toy model, which is a very typical academic model that's widely used. And it's a predator-prey model where you have two species. One species is the prey, and we see that the prey has some growth rate, and the other species is the predator, which has a death rate. And the predator and the prey, they interact, and the three parameters in this model are alpha, beta, gamma, delta. And typically one thing that we want to do is, for example, fit these parameters to time series data. And so this is basically an ODE once we specify the initial condition, but we might have more complicated scenarios. For example, maybe we have additional species that we can't model that well, so we include them as Brownian motion terms, so we have stochasticity. Or we might have events, for example, we shoot wolves at a specific time, or could have delays due to the interaction between predator and prey. And just to basically give you a bit of schedule for what the goals are for this presentation, First, we will do parameter inference for that model. Then we will discuss model selection and discovery. And then we will basically do something that's probably even a bit more complicated, which is like stochastic optimal control for that model. And yeah, we will consider slightly different variations of the predator-prey model for these things. So this predator-prey model is also called the Lotka-Volterra model. And we can easily write this in SciML, the ODE function, which takes as inputs the states, the parameters, and the time. So this is the right-hand side of the ordinary differential equation, where we have the first state is the population size of the rabbits. The second state is the population size of the wolves. We have the parameter vector. Here's a 4-dimensional vector having all parameters. We compute both rates, and then we return them as a vector again. To solve this kind of ODE problem, we need to define the time span over which we want to solve it, an initial condition for the population size of the rabbits and the wolves, and like some parameters for alpha, beta, gamma, and delta. And these will be like what we consider in the following our true underlying parameter values. So just to show you, this syntax for writing a vector is really, 2-dimensional vector. Once we have defined this ordinary differential equation problem, we can easily solve it. And the SciML ecosystem offers tons of ordinary differential equation solvers. For example, we can use some easy explicit Runge-Kutta method, which might be good for non-stiff equations. And if we don't specify anything, we will get a solution object back that says if our solving was successful, we will get some sort of interpolation. And by default, it will just store the time points for which the solver took for like the steps. So here the solver took, I guess, 12 steps from like the initial time to like the final time 5, and it returns all the states that it had on the way. We can use more sophisticated solvers. We can set tolerances, for example, here low tolerances if we want to solve it to a very high accuracy. And we can specify at which time points we want to store the solution. So in this case, we specify that every 0.25 time units, we want basically to store the solution object, and we get this back here as the solution. The whole thing doesn't only work for ODEs, but it has a very similar interface for stochastic differential equations, delay differential equations, and other things of, other sorts of differential equations or in general numerical problems. So we can have, for example, simulate a stochastic differential equation by providing also like a diffusion function. We will see something very similar later in more detail, so don't worry about it maybe for now too much. But you see, we just, instead of an ODE problem, we define an SDE problem. We need to parse some additional parameters for P5 and P6, but then we can use some higher order stochastic differential equation solvers. We can simulate this a bunch of times, maybe 20 times, and we see, we get different trajectories depending on the specific noise realization of the system. Also, very or highly needed in typical application is like handling of events. For example, we might have in our model something like, specify specific conditions. For example, we might have a reduction of the wolf population at specific times. So for example, this means that when this function evaluates to 0, so when the population of the wolves is equal to 1.8, we will apply the following effect to the state of the ordinary differential equation. And this is decreasing the population size by 0.2. And we can easily have this event defined by a so-called callback that we pass to our solve call and plot the solution of this. And what we will see is that, when we reach 1.8, as we defined, we basically have this sudden event happening in the time evolution. And similar to these kind of implicitly defined events where we have to do some route finding procedure to find the event location, we could have explicit events where we just give like, specific time points, for example, when a controller would be updated. And you can have many things that simplify simulation and modeling. For example, parallel ensemble simulation will allow you to easily set up your problem to solve multi-threaded in a multi-threaded way several trajectories, which we will see later actually for like stochastic differential equations. And some very recent developments here for like what tools are there for simulating different kind of problems. We're working very actively on nonlinear solve GL, which will provide very fast Newton solvers to solve nonlinear systems. Here's a maybe easy slide, but very important slide for the rest of the talk. So this is basically the high-level overview of what we do in all of these examples. And the procedure is basically, well, we want to set up or formulate our inverse design task as some sort of optimization problem. And we do this by first defining a loss function that encodes our specific objective and some constraints that we want to fulfill. Then one very important step is to compute gradients. And the most important thing here is to highlight that all these solve calls are basically compatible with AD. So we will see later how this leads to like computing gradients is very easy, but under the hood, a lot of things will basically happen. And then we can use, gradient-based optimization methods such as ADAM, LBFGS, or just stochastic gradient descent to optimize 3 parameters. And if we really want like an interpretable interpretation of whatever we optimized, we might want to find some sparse symbolic form. So yeah, let me first generate some training data. So we have here this solution object from before, which I solved by this. So the ODE problem actually, which is solved forward in time. And I just add some, very small amount of noise. The specific noise form here is not very important. So we see the solution of the ODE, and in the following we consider these data points here as the data that someone handed to us, basically. So yeah, to fulfill the first step, actually, so the setting up a loss function, we might want to do the following. So we want to pass to a loss function the current guess of our parameters, and then we want to predict the time series given that set of parameters and compare, the whatever we got as a prediction with respect to our true data, potentially under some L2 norm, an L2 loss, which is here just this 2 norm. And this predict function can be written very easily. So we take in the parameters, we redefine the ODE problem. We can again just simply solve it with some specified tolerances, save at the same time points where we have basically the data. Note that this doesn't need to be equally spaced. Whatever you pass here, you simply have to match the points of the data, and then you can convert this to an array to only get the states and not like the full solution object. Now, why are derivatives for this loss function, for example, important? The first thing where derivatives usually show up is that you want to do something like sensitivity analysis. For this, you could, for example, imagine that this loss function is not comparing something to data, but maybe only considers the population size of the rabbits at the final time. And then we might want to ask some question, how does this population size change with respect to changes in the initial conditions or the parameters? Then another big reason for getting derivatives is like in some numerical methods, we just intrinsically need to compute derivatives, to use these methods. For example, in Hamiltonian Monte Carlo. And the big focus of this talk will be basically parameter inference and control, where we want to tune the parameters to match the observed data, or we want to tune parameters of a controller to drive the system to a certain final state. And I will make the claim that computing derivatives will always be easy when we can solve everything analytically and just compute analytical derivative of the analytic form of the loss function with respect to the parameters. But here, of course, we now only have access to like this computer program, and we have only like implicitly defined, through the steps of the solver, what the final loss function value is. One easy way to compute derivatives is basically using finite differences. So finite difference we would say maybe we have an initial guess of our parameter, and we compute, by numerical differentiation, we perturb the first component a little bit and get the value out of the derivative by, perturbing it a bit, computing loss value for like this value plus epsilon minus the loss value of this value divided by epsilon. And in this way, we get this numerical derivative out. In this case, this works quite nicely because, for a first reason, this vector is very small, because if this vector is large, we would have to perturb each of these values individually. So it scales badly with respect to the number of parameters. And for another reason, this kind of adding small differences and dividing by a small number, or subtracting two values which are nearby divided by a small value, can have like numerical problems due to floating point errors. So a better way to do that is to use forward mode AD, which gets at least rid of the floating point issues, but also scales poorly with respect to the number of parameters. And an even better way, if we have like a large number of parameters, is to use reverse mode AD, which can be used by just using any reverse mode AD package. And you might wonder, how is this possible? Is this always possible just to call some reverse mode AD package on these loss function? And here I want to say that really a lot of things are happening under the hood in SciML sensitivity, basically. And there are, in principle, two ways how SciML sensitivity computes derivatives for solutions of differential equations. The first one is called discretize then differentiate, which basically is what you might have expected. So it's like, computing or applying automatic differentiation on each step of the solver individually, and then using the chain rule to backpropagate or push forward basically sensitivities to compute in the end the full gradient. Or we can have this differentiate and discretize paradigm, which basically means for an ODE system, we derive another augmented ODE system, which we then have to discretize in a second step, for example, by some ODE solver, which will give us an approximation of the exact gradient. And the first one gives an exact gradient of the approximation, and it's not always clear which of the two you want to use. And there are, a lot of trade-offs that go, where many people analyze which one is better for different systems. And even more, both of these basically ways or paradigms come with two modes each. So it's like both of these have typically like a forward and a joint version. And I think the most important thing here is to realize the optimal choice will for sure depend on the number of states and parameters, and in particular also some system-specific properties. So there's no method that fits all purposes, but a good rule of thumb is to use forward mode approaches when you have like a small number of parameters. So 100 is actually like a very conservative guess here. So some people put here like 1,000 parameters. And just if you have very large number of parameters, for example, if you're using neural networks, then you go to something like reverse mode AD. And I don't want you to pass all the available options in SciML, but just to give you like a feeling of what's kind of available. There are different of these methods for all purposes, which have different implementations. Some of them are more stable, some of them could be more performant, maybe because they have like a lower memory usage, or like they can be used on GPUs. Yeah, and so it's basically a trade-off between stability properties and performance, which one you want to use. And at the moment, we're actually actively developing on like an improved version of one of the existing methods that should be GPU friendly and also more memory efficient. And we think, or we hope at least, that this method will be like a very good default for many systems. Now, to do Now, let's first do parameter inference on this ordinary differential equation system. So for this, I first define a vector for my stored loss values, just to plot them in the end or like track them during training. And I define a callback that can be passed to these optimization functions. So in this callback, I simply say, well, every 50 values of the iterations, I will print the current loss value. And then, you can use optimization.jl, where you say which of these AD modes you want to use. You define the specific optimization function, which in our case simply means, optimize the loss with respect to the parameters. We pass this to a so-called optimization problem, and then you have basically, again, the same kind of interface. You just call optimization.solve, and you have this, you can choose any optimization solver you want to. Here I use Adam because it's just, it's a fast method because it's like just first order stochastic gradient descent. And, we can easily run this. And for, a logical Volterra model, this will run very quickly. And so we can run maybe 10,000 iterations here and track the loss value, which starting from a value of 59 quickly goes down to something like 0.005. And we see that we recovered from some initial guess of our parameters, something that's very, very close to like the true parameter values. So this is basically the pipeline, how you could do parameter estimation for ODEs. Now we go one step beyond the simple parameter estimation when you know the full structure of ODEs. And we discuss a bit model selection and discovery, which is very close to what Vinicius showed you in the talk before. So we will use this paradigm of universal differential equations, where we will use some kind of universal function approximator, and neural networks are just a good choice for that, inside of a differential equation to model all sorts of terms that we don't know. So for instance, we can have this slightly modified predator-prey model where we say, oh, we know the growth rate of the bunnies and we know the death rate of the wolves, but maybe we don't know how they interact. So we use a neural network with two outputs, where the first output should correspond to this term, and the second output should correspond to the second term. And the same is basically as before. We can use Lux in Julia, which has like a very nice documentation. It's very easy to use to set up a neural network. So for example, we can have like a very shallow neural network where we get the two states, so the population size of the bunny and wolves as input. We do some fully connected layers to finally get, two states as the output. And we can easily define, whatever activation function we want to be applied after each layer. Then we can define this universal differential equation model by the same sense or same manner as before. We give as inputs the states, the parameters, in this case now the parameters of the neural network and not of the ODE at a time point. We can here write, if we want, directly alpha and here, delta, which are the true parameters that we assume that we know. And if we want to write it slightly more efficient than the previous version, we might pre-allocate the rate vector to directly write into a rate vector at each of these update rules. And then we can have a closure which passes these true parameters here in this form, also just to be slightly more efficient. And then we define here in this line the ODE problem again, which now has this vector field. We have an initial condition that we know from before. We use the same time span, and this P are now the parameters of the neural network. And again, as in the parameter inference part, we basically do exactly the same. We use a predict function where we feed in like parameters. We remake the ODE problem again, in this case, with the parameters of the neural network. So what we might want to do is help SIML sensitivity to fix a good of these sensitivity options, but there are actually pretty good heuristics in the package that would automatically choose for you a good method depending on the size of this parameter vector. And then we again get the states as a function of time and compare those states to like the true solution data as before. And also the optimization is exactly the same as we did before, with one small detail here, and that is Lux actually gives us a named tuple of parameters. So we wrap those named tuple into like a vector, but that's really just a small technical detail. Then we can again track what our optimization is doing. And in this case, in the first epoch, we have a very, very high loss because obviously the neural network function is not even close to like the true term, but Adam manages to quickly push down the loss. And then a very common strategy is start with Adam, but then use a few epochs of a more sophisticated optimization routine. For example, LBFGS, which is like a quasi-Newton method that that computes like an approximation to the Hessian on the way, and so kind of it's more sophisticated to find local minima. And we will see in a moment how this looks like. So this takes some seconds more, but we will only do 1,000 iterations in this case with our neural network. So this is really like to push down the loss from something here like 0.5 to hopefully much smaller values. Yeah. So we see like the first thing was a bit of compilation time and then printing things, but then you see LBFGS manages to very quickly converge to something like 1e minus 5 as the loss values. We can actually visualize this improvement. You see like Adam very good here at bringing it down quite far, but then kind of separates. And then we could also try to reinitialize Adam, which sometimes can also work. But just using LBFGS, we very quickly reach then a much smaller loss value. And just for comparison, we can check if the neural network does well by taking the predictions of our neural network with the trained parameters and comparing them to the true measurements, where we see that the neural network trajectory now also fits the data nicely. And we can even easily compare the analytical solution of the interaction term with respect to the neural network solution. And I mean, as expected in this case, you see that they nicely overlap. And also like the L2, you can look at the error basically of this reconstructed interaction term with respect to the true analytic solution. And I think at this point, we might be happy because we found something that fit our data, but still, sometimes we want to go one step beyond just fitting the data and really understand what this neural network guess corresponds to. And for this, one good solution is to try to get like a sparse symbolic representation of the missing equations. And we will use data-driven DiffQ to do that. And one first thing that we need to get like a symbolic representation of the missing equations is to define a symbolic basis. So we can easily do that by using data-driven DiffQ. And for example, we say, well, just use a polynomial basis here. And this is basically the basis in which we want to, reinterpret what the neural network is doing. There are lots of details, and I can't actually go into too many of them, but to give you just a sense of what you typically want to do. I would say maybe the most naive way, but also like the full problem way, if you want to try maybe first, is what if you didn't train a neural network and you try to automatically uncover like the equations from this kind of original noisy data. This is the approach, or an approach that's very similar to Cindy, which is very often used, I would say. And Cindy simply tries to approximate the ODE function by using finite differences between the data points. You can also already see that this has problems if you don't observe all your data, and also if these points are fairly sparse, right, in time. And then the point here is to, you want to find a set of parameters for these basis functions, which could be, anything from like polynomials or monomials here, and like sine, cosine terms, whatever you think makes sense for your physics. And you want to enforce sparsity of these coefficients to recover like a sparse interpretation in that basis. We might compare that, if we know the true solution, to like the ideal right-hand side missing function. So, which is like, usually we don't know that f, right? So I want to stress, if you don't know that f, that's not possible, of course. But if you know that f, you can at least compare if all these data-driven sparse regression methods will work. So you compare it to, the true value of the derivative and try to still do the sparse regression here. And the thing that you actually want to do probably is to use the neural network problem, where you try to come up with like a symbolic representation of the neural network using that basis expansion. And one thing that's a bit sad here is that this full Cindy problem takes actually a bit too long to solve, so I can't show it to you. And also in this case, I couldn't make it fully work, so it just doesn't recover the good sparse solution. So it's a bit more too complicated, I think, already. Or at least you would need to tune more hyperparameters, and all that kind of stuff. And so I will focus here on two things. So this ideal problem, which typically is unavailable in practice, but just, a check that everything works. And the neural network problem, which you can try to do, right? So trying to find a sparse representation of your neural network. To solve these different optimization tasks just defined, we can use some method from the data-driven DiffyQ package. I will use ADMM, but if you look, at the data-driven DiffyQ documentation for sparse regression, then you see that there are other methods, for example, the one from the original Cindy paper. ADMMM is the one we're using, but also even more like SR3 and other methods. So we can, define some options. I don't think you have to worry too much about the options that I'm defining here. Those are just, for reproducibility in the talk, and like to see that everything works here. Very similar to the other things. Once we have defined one of these data-driven problems, we simply have a function that's called solve. We pass in the basis and the optimizer, and then we will get out, basically the solution. We do the same for the neural network problem. So one-to-one the same. And we see already that the residual here is slightly higher. And we can print these resulting sparse regressions. And we see the first part here are the ideal equations, where we see that we recovered really the right symbolic terms, though we have some mismatch here in the parameters. And that's due to solving slightly different optimization problem, where we have this additional like Roche multiplier for like enforcing sparsity. And we have also here the solution for the neural network, where we see, the neural network also recovered, we recover using the sparse regression, the good terms, or the terms that we expect from the true solution that we know in this case. But we might also recover some spurious terms, right? So it's not guaranteed that this will really yield the true underlying terms, in particular if, noise is large, you have very sparse observations, etc. And also we see actually that the parameters are slightly or somewhat different, right, to our like true solution. So what we always should do is to check how our recovered model performs on the data. And in this case, I plot again the data or the ODE trajectory underlying the data in the dashed lines and the estimated model in the solid lines. And we see that after recovery, well, we actually don't fit the data anymore that nicely, right? So it's like we knew the neural network fit the data, but we see the recovered model with the parameter guesses actually doesn't fit the data well. And so the common thing that people are doing that's sometimes like not mentioned is that you can then fine tune the parameters by trying to fit again the recovered sparse symbolic regression with like these 5 parameters to match the output of the neural network. If we do that, so we simply run this optimization in the same way as before, we see that all those parameters from the terms that we don't want to have in our model basically go to 0, and the other 2 parameters, so which were previously beta and gamma, I believe, match now with the neural network form. So then we would check again, right, if it fits the data, and then if it tries to extrapolate, or if we try to see if like extrapolating to larger times would also work. In this case, it's basically trivial to see that because we know the true solution and we know that it fit has recovered the right parameters. I also want to quickly cover stochastic optimal control, which is like a third thing that you might want to tackle as like an inverse design problem. And in this model, for example, you might be interested to design a policy that controls the population size of wolves and rabbits. So I will use here a stochastic predator-prey model where we have like the same model parts as before, but in addition we have a controller that allows us to reduce the number of wolves, and we might assume that there's like a third species which is maybe a predator where the exact interaction with the rabbits is unknown. So we just model it by including this kind of Brownian motion that randomly varies the rabbit population. And obviously that also randomly influences the wolf population because these equations are coupled. And we also might want to say, well, our controller should not be infinitely powerful, so we might restrict the controller to the range 0 and 1. The rest is again as before. Basically, we define like a time span, initial condition in this case. We have now 5 parameters with the same 4 as before, and then we have also like a parameter for this for eta, which was this scale of the noise basically. We define our controller again, very similar, taking the 2 states as input, doing some intermediate functions, and having one output in this case, which is the value of the control drive, and we map that value to the domain 0 and 1. The UDE in this case is like a universal differential equations based on like a stochastic differential equation. So we use the controller, the neural network in this case, to predict the control drive value. We again construct the drift of this differential equation, which basically looks as before. And we add, in addition, the diffusion function to build the full SDE, where we see that the diffusion is this multiplicative noise for the first component. And we again build then the drift and the diffusion by passing the true parameters that we assume to be known. And in this case, we want to optimize the parameters of the controller. We can basically verify that if you just randomly initialize the controller, we will have these stochastic trajectories. So I plot here 100 trajectories for the dynamics of the system. We might want to say, let's regulate the number of rabbits or the population size of the rabbits to be 0.75 and the population size of the wolves to be 0.5. And we see, well, a randomly initialized controller doesn't do that. And here I want also to highlight, we use this ensemble problem interface from before, where we can easily say, wrap this SDE problem into an ensemble problem and then simulate in a multi-threaded way 100 trajectories. To incorporate or like encode our objective, being population size of the rabbits equal to some number, population size of the wolf equal to some number, and maybe some additional regularization term on the controller. We do the same as for the parameter inference in the model discovery part. We define this prediction function we remake the SDE problem in this case using the new parameters in each step. We solve this for several trajectories using the ensemble problem. We convert the solution object to an array, and then we define the loss function to match this stage cost. And this looks basically the same. Let me go once forward and back. So we have, in this case, I again define basically the losses to be initialized. Like as a vector, I add a callback, and you can easily track progress during training by, either as before, we store the loss function values and print that value after, some specific amount of iterations always. And we can also add in addition, like, a plot in each of these steps just to check if we have, visual progress also during training, and it seems to do the right thing. The rest here otherwise is the same as for the model discovery part. So I started here this optimization. It takes slightly longer than before because, in this case, we need to solve not only one stochastic differential equation, but several stochastic differential equations in parallel to find the optimal controller. And the neural network is also, I think, a little bit deeper actually, or like has more parameters than before. But yeah, we can, when we track this, we see this was basically the initial dynamics of the population with like this randomly initialized controller. I think it gets already a bit better after 50 iterations. The loss value goes down, a little bit here for like 100. And I think if we wait a little bit after 150 or 200, we see that, this dynamics gets closer and closer to like the population size that we want to reach. And I think actually after 500 or something, it's then already converged basically. Let's wait maybe one more to see did it even go further down. Yeah, maybe I let it run and we can come back because I don't have much more things to say. I want to give a very quick overview without going into too much details what we're currently working on, because this maybe gives the impression you can do everything with these kind of tools and there are no further issues. But of course, the Lotka-Volterra example is kind of a toy model. So you can run into problems, and I want to highlight two problems that we actively are currently addressing, at least, out of quite a lot of ongoing research problems. One thing is, what if your dynamics is actually chaotic? And without going into too much details, you might have this Lorentz system, which exhibits this famous Lorentz attractor that you can, oh, okay, my neural network is still training. Slowing this down a little bit. Okay, so let me just introduce the system here. So we have the Lorentz model has like 3 states in this case, and a single free parameter, which is this parameter rho here. And this model exhibits chaotic dynamics, meaning that if you simulate it long enough, then small variations to this parameter or the initial condition, or also parameters of your solver might lead to like a completely different trajectory, which is known also as like the butterfly effect. And in this case, you can easily imagine, right, that if you want to do sensitivity analysis, you will also get like extremely large values because like small changes lead to extremely big differences. But, okay, so this is like the famous picture of this Lorentz trajectory of how the dynamics look like. And this is a visualization of this butterfly effect where you simulate it in exactly the same way. And you get very big differences, even if you fix everything, but just very deciding on, if you use float 64 or float 32 for like your the simulation of your system. But even though the system is chaotic, some quantities are well defined. So for example, there are long time average quantities where you have like an instantaneous objective G that applies like to the states and some parameters, and you average that objective over time. For example, in the Lorentz trajectory, we might consider just the Z coordinate and then look what happens for like very large times. And under some assumptions for chaotic systems, for example, ergodicity, we actually know that this quantity only depends on the parameter theta. And the nice thing, what comes out, or what we actually observe, is that despite Z of t being this chaotic function, highly fluctuating, when we look at the long time average quantity of Z, then we see that it has basically this very nice or well-behaved curve here, where we see that the slope actually of this curve is almost always equal to roughly 1, right? So it goes here from 10 and 10 to roughly 50, 50, and 50. So we would expect for this long-time average quantity to get a value of the derivative of Z, of average Z, with respect to rho to be 1. But if we apply automatic differentiation or like finite differences, then we actually get very large values, very large positive values, very large negative values that just don't match this expected value. So what we're currently also developing is tools that regularize this AD computation to subtract all of these butterfly effect kind of things and focus or allow you to actually distill the effect of shifting the attractor, which happens as a function of rho. And these tools are called shadowing methods, and there's like I have a blog post which goes into detail how they work, what tools are available. But if you apply these tools for the sensitivity computation, you see that you get a value of 1 as you would expect. Yeah, I don't want to go into too much detail for like other failures, but I think that's a nice point to conclude this talk. So I hope I presented you some SciML contributions. In particular, SciML offers some very good solvers for various sort of problems, unified interfaces. So it's pretty easy to, if you're familiar with solving ODEs, to go to solving SDEs and other scientific problems. It allows you to very seamlessly, like easy, combine these kind of scientific models with data-driven machine learning models such as neural networks, and provides also very easy workflows for like doing parameter inference, model selection discovery, and also optimal control. Yeah, thanks.